Hey everyone, welcome to APSC 174. Here we are. I am just opening the Q&A. Some of us just met yesterday. So here we are. That's the chat. So here we go. So APSC 174 after APSC 172 yesterday. Welcome. My name is Antoine. You already know this. My email, which I hope also that you know, Antoine@prep101.com. And I will be working with you just like we did, honestly, it seems like 2 weeks ago, a bit like less than 2 weeks ago, on the material that was on midterm 2. So the session plan is as follows. First of all, I pre-recorded and they should be available for you. I pre-recorded a lot of stuff. I'll show you. I recorded for you all of these topics. So vector spaces, subspaces, spanning linear independence, like all of them you could read. So I did tons of problems and I made a big effort. So the problems are not the same problems as the ones that I solved in midterm 2 or in midterm 1. And sometimes we solve the same problem. It's inevitable, or sometimes it's by bad luck, but I tried to make it all new problems from new sources, so you get extra practice for this. The video for this is already up, I'm told, or if it's not up now, it'll be up very, very shortly. There's some really nice problems, some really good review of these topics. So this is already done. I hope that you get a chance to watch it. It is ready, and I'm told it's, I mean, maybe you can check now. For APSC 172, for sure it's up. For APSC 174, I was told it was going to be up, but I didn't get a final confirmation. So those are done. And anyway, we did those 2 weeks ago. For the final exam, the plan is as follows. I'm going to cover mainly those topics which overlap. I mean, this is new, the matrices, so let's put an N next to it. This is new. This is new. And this is new. Those are partly new because we did solve some of them for midterm 2. Then my focus will be to begin here. I'm going to do determinants. I'm going to do eigenvalues and eigenvectors. I will explain to you matrices and their inverse and all that. And then I will go back and I will talk about linear transformations, the image, the kernel, the basis, all that. Then I will talk maybe before that when after we do matrices right away, I'll do systems of linear equations. And then I am going to solve as many as I can, as many problems as I can, covering these topics. I will not include detailed explanations of all this because I already did this in the pre-recorded part. So there's no point in doing the things twice. You can watch the pre-recorded part. For this part right here, it's going to be mostly problem after problem after problem. As always, you can always ask, right? So let's say I did a problem on linear independence, and then you say, you know what, I'm not really clear on this. Can you just say that again? I will be more than happy to re-explain it or to talk about it or to give you another version of it. By now, I think you've taken several sessions with me. You know that I 100% adapt to you rather than ask you to adapt to me. So I have a general outline for the session, but it's nothing that we can't change to help you. I mean, this is basically for you, right? It's, I mean, partly for me because I'm getting paid, but mostly for you because you want to ace your test, right? So I'm 100% dedicated to what you guys need to ace your final. How was midterm 2, by the way? Easy, difficult, as expected? How was the session compared to the midterm 2? You know, those are things I really like to hear from students. Did you think we did okay? Did we cover topics that showed up? Did we cover things that were very, very close? If you tell me these things, then I know how to adjust my session today, how to, you know, recover things, not cover things. Again, any input from your end would be appreciated. And if you don't want to do it in the Q&A, you can always send an email, right? So otherwise, the session is recorded like all the sessions before it. The recording will be available. Today's recording will be available tomorrow. Tomorrow's recording will be available Thursday, and my notes, my awesome notes, will be made available to you on tomorrow after the session at 9:30. As usual, as we do in 4-hour sessions, we're going to take 2 breaks. They're scheduled to be 20 minutes each, but we might make one of them 15 and the other 20, depending on the level of fatigue. We'll see. Do you have any questions for me? Do you have any comments, any final requests, any wishes before we begin? There we go. Cheers. Orange Crush. And it begins. So let's begin with determinants. So that's one of the new topics. Oh, by the way, I don't know if you care or not, but I was planning on solving for you one final from beginning to end on the recorded part of the session, but I didn't have time. The 4 hours ran out, so I still did solve it, but it's here. So this is my solution of I chose 2018 final, so I am also going to share that with you. You do have the solutions of your teachers, but I mean, these are my solutions, and if we have time today, I would like to repeat the experience, get a final from beginning to end, and then solve it from beginning to end, to give us kind of an overall review of everything that's happening on the final. If we have time tomorrow at the end, I would very much like to do that. If you have a preferred final you would like me to solve, then email it. Again, you tell me and I will help you. Cool? So, determinants. What is the notion of determinant? First of all, we take the determinant of a square matrix, of a matrix A that's n by n. So of determinant of a n by n. So that is what we call a square matrix. Same number of rows as the number of columns. And the determinant of a matrix is a number. It's a number that is very, very, very important. It tells us a lot of things about the matrix. I will show you in some of the theorems that we will write, and some of the theorems that we will repeat actually several times, how important the midterm, my chair keeps moving, how important that number is. For a 2 by 2 matrix, this is the simplest of cases. The determinant of a matrix that is A, B, C, D is AD minus BC. Is AD minus BC. Right? So for example, let's take a simple example. The determinant of the matrix 1, 2, 3, 4, that would be 1 times 4 minus 3 times 2, which is minus 2. Great. Now, for a matrix that is 3 by 3, there is a shortcut. Students like it. I don't like it very much. So there is a shortcut and there is a general method. So I'm going to tell you what the shortcut is, and then I'm going to tell you what the general method is. So you write down your matrix A, B, C, D, E, F, G, H, I. Then you recopy the first 2 columns. So you copy A, D, F, and then B, E, H. Then you draw 3 arrows down and 3 arrows up. And you remember that down is plus, up is minus. So it would be the determinant, let's call this matrix A. So the determinant of matrix A is down is plus, up is minus. So it's plus A times E times I plus B times F, that can't be F, ABG, sorry. And then BEH, right? So A times E times I plus B times F times G plus C times D times H minus G times E times C minus H times F times A minus I times D times B. You've seen the arrow shortcut? So for example, what would be the determinant of the matrix 1, minus 1, 3, 2, 2, minus 3, minus 1, 0, 2. So what we do is we copy this 1, minus 1, 3, then 2, 2, minus 3. Then I put 3 arrows down, 1, 2, 3, and then 3 arrows up, 1, 2, 3. So the determinant is equal to plus. Now down I have 1 times 2 times 2 plus 2 times 0 times 3 plus minus 1 times minus 1 times minus 3. Then minus 3 times 2 times minus 1 minus 3 times 0 times 1 minus 2 times minus 1 times 2. And the rest is just algebra. So this is 4 plus 0 minus 3 plus 6 plus 0 plus 4. So that would be 1 plus 10, 11. And that's how we do the determinant of a 3 by 3 matrix. Sadly, this only works for 3 by 3. Now, for any n by n, now this also works for 3 by 3, it works for 2 by 2. For any matrix that is n by n, what's the general method of finding the determinant? That method is called the Laplace expansion. I prefer to call it the cofactor expansion. I'm used to the name cofactor expansion rather than Laplace, but call it whatever you want. Now, to be able to do this, it's very important to remember the sign matrix. It's very important to remember a sign matrix, a certain sign matrix. It's a very easy matrix. It starts with a plus and it alternates in all directions. So plus, minus, plus, minus, plus until the end of time. Then minus, plus, minus until the end of time. So the second one, it alternates. So plus, minus, plus until the end of time, right? So dots, dots, dots. So there's a reason why this is, but we're not gonna go over it because usually they don't cover that in 174. They just need you to remember that just the sign matrix and that's enough. So look at how we do this. The determinant of a matrix A is you decide to go over any row or any column. So you take the sum over any row or of course any column of the sum of what? Of the entry, well, actually, let's use first the sign of the sign which you get from the sign matrix times the entry times the cofactor. So you tell me, okay, Antoine, what is the cofactor, right? The cofactor, okay, realistically, the sign should be included in the cofactor. Now, let me be clear. I'm doing this APSC 174 way. In general, it's entry times cofactor. In January, there's no sign. The sign is part of the cofactor. But because APSC 74 does it that way, I'm just going to do it whatever they do it. So what do I mean? Let me give you an example. Let's use the same matrix. Oh, we destroyed that matrix. But I'm gonna try and save it. So what is the determinant of this matrix? Please pay attention. Again, we're not yet at the theory part of this. We're just doing calculations. How do we calculate the determinant? Very shortly, I will tell you why do we do this, what's the application of this. We're going to do tons of theory, but just in a second. So, pick a row or a column. First person to say something, I'm going to do what they say. Pick a row or a column. No? You'd like me to do it? Column 1, Johnny says. Hey, Johnny. So Johnny would like the expansion on column 1. Let's do that. By the way, Johnny, usually choose a column or a row that has zeros in it. That's more beneficial to you. Usually, we choose the column or the row that has the most zeros because that simplifies your calculations. Okay, but you said column 1 and I stand by what you say. So we're going to find the determinant along column 1. Okay, I'm going to write this as a note. Usually we choose the row or column with the most zeros. All right, so let's do this. First thing you got to remember is the sign matrix. What's the sign matrix? You start with a plus, so you have a plus, minus, plus. I'm going to tell you how to use this. So you say plus, sign, entry, cofactor, plus 1. The entry is 1. The cofactor is what? The cofactor is the determinant of the matrix after you remove the row and column you're at. So it's the determinant of 2, 0, minus 3, 2. Then minus, sign, entry, cofactor. The entry is minus 1. The cofactor is determinant of, cancel the row and the column you're at. You will get 2 minus 1 minus 3, 2. Then sign plus entry, cancel row and column, you get the determinant of 2 minus 1, 2, 0. And you know how to find each one of those determinants because they're 2 by 2. So this is 1 times 4 minus 0 plus 1 times 4 minus 3 plus 3 times 0 minus minus 2. So 0 plus 2. So the answer is 4 plus 1 plus 6. And what do you know? The answer is 11. Would it matter if we chose a different row? Would it matter if we chose a different row or a different column? No, it wouldn't. It would not matter at all because you can choose the sum over any row or any column. This is what you call the cofactor expansion. This is what's referred to as the cofactor expansion. Now, let me show you why this method is terrible. Theoretically, this is a great method, but practically, this is a bad method to find determinant. And then obviously, I'm going to give you the alternative. So what do we use if we were asked to find a determinant? So let's say they ask you to find the determinant of, and they give you a matrix as small as 4 by 4. So let's say 4, 1, 0, 2, minus 1, 3, 1, 1, 2, 1, 2, 1, 0, 1, minus 1, 5, whatever. Great. How do you find this determinant? Again, pick a row or a column. Now let's pick one that has 0. So let's make the right choice. So would you like column 1, row 4, column 3, row 1? Do you have a preference? You don't seem to have a preference. Oh, column 3. All right, Brooklyn. So column 3. It's funny you guys chose the same thing. So this would be what's the sign matrix? So you have plus, minus, plus. So I don't need those. Then it's minus, plus, minus. So it's plus 0 times who cares, right? When it's 0, we don't say times the determinant, blah, blah, blah. Who cares? It's 0, right? Then minus. The entry is 1 times the determinant of, and then I'm going to cancel the column and the row of 1. That'll give me 4, 1, 2, 2, 1, 1, 0, 1, 5. Then plus sign, entry, determinant. Cancel the row and the column that I'm at. So that'll give me 4, 1, 2, minus 1, 3, 1, 0, 1, 5. Great. Then the last one is going to be minus the entry, determinant, cancel the row and the column. That'll give me 4, 1, 2, minus 1, 3, 1, and then 2, 1, 1. But the problem is, and you may have guessed it, this is terrible. Now you still have to do this. And you still have to do this, and you still have to do this. This is very long. Like, this is very long. There must be an easy way to do this. And what I'm going to show you now is how do we find the determinant using a fast method, which we won't scrap this method completely. We're going to use this method, but we're going to combine it with something else that would make this method go much, much faster. Are you still with me? So now I'm going to build up some knowledge before I give you the next method. All right. So first, a couple of notes or theorems or whatever you want to call them, some things that we absolutely must remember. First of all, if we have an upper triangular matrix, what's an upper triangular matrix? In a square matrix, we call this the main diagonal, like the entry that row 1, column 1, row 2, column 2, row 3, column 3. This in a square matrix, so I'll put this on the side. So if you have a square matrix, this is a matrix that's n by n. This right here, this is called the main diagonal. So a matrix is called upper triangular if everything below the main diagonal is 0. So everything below the main diagonal is a bunch of zeros. 0 with an S is 0, or you can just put 0. A matrix is a lower triangular matrix you've guessed it, if everything be above the main diagonal is 0. And a matrix is diagonal, and we love diagonal matrices. You don't do enough in them in this course, but I guarantee you your next linear algebra course will have to do a lot with diagonals. So it's everything that's off the main diagonal is 0. Now there could be zeros on the diagonal. We don't care. We're just not looking at the diagonal. We're looking anywhere else. And why do we care about those matrices? We care about this matrices because the determinant of an upper triangular or a lower triangular or a diagonal matrix. So when you find the determinant, if your matrix is upper triangular, lower triangular, or diagonal, this is equal to the product of the main diagonal. So you take the entries on the main diagonal and you multiply them. Let me give you an example. So what's the determinant of the matrix? 1, 2, 3, 0, 5, 1, 0, 0, -3. Can we see that this is the main diagonal? Everything below the main diagonal is 0. So this matrix is upper triangular. The determinant of an upper triangular matrix is the product of the main diagonal. So this is minus 15. Okay, are you ready for something more? I know we didn't do them yet, but we will do them later today. If a matrix is upper triangular, lower triangular, or diagonal, not only the determinant is the product of the main diagonal, the eigenvalues, this is for later, but the eigenvalues are the entries on the main diagonal. Again, we're going to do more about this later, but this is like a sneak preview. The eigenvalues are basically of this matrix are 1, 5, and minus 3. That's how much we like these triangular matrices. It's rare that we get them, but once we get them, they are pretty awesome. What would be the determinant of the matrix that is 5, 0, 2, 1? This matrix is lower triangular. I mean, this is very simple. You can see that the answer is automatically 5, but I'm just being cute. What's the determinant of this matrix? 1, 0, 0, 0, 1, 0, 0, 0, 1. Do you recognize this matrix? What is this matrix? This matrix is a very important matrix. This is the identity matrix. Why do we care about the identity matrix? Do you know this? Why is the identity matrix of importance at all to us? Because the identity matrix, I, we call it I, this is the identity matrix. We're going to say this later, but I like to just give you the whole picture right away. This acts like a 1 in matrix multiplication. So this matrix times any other matrix, you get the other matrix. It is literally the 1 of matrices. So the determinant of the identity, because it's diagonal, it's 1 times 1 times 1, which is 1. Right? So that's the first step in getting a new method that's very, very good, very fast to find the determinant. Now, if we can get the matrix that we have to one of these forms, this or this or this, then the rest would be very simple. If we can magically transform our matrix into an upper triangular or a lower triangular or a diagonal, then the rest is very simple. But wait, we can transform it to this. This form, upper triangular matrix, that's REF, isn't it? So that's very, very close to REF, unless you want to make those entries 1s, right? The 5, you want to make it a 1, and the 3, you want minus 3, you want to make it a 1. So this is basically the same process as getting to our REF. So yes, we can get our matrix to become one of these, but there's a price to pay. We're going to do operations. So we're going to do some operations on the matrix to transform it to become this. So we need to study the effects. What is the effect of elementary row operations, EROs, elementary row operations, on the determinant? All right, so what are the elementary row operations? So here we have a matrix A. We apply an elementary row operation, and now we get a matrix B. Our interest is how do the matrices, how do the determinants of these matrices connect? So if the operation is switching row I with row J, because that's the first operation, then the determinant of B becomes minus the determinant of A. So you multiply the determinant by a minus. if the operation is multiplying a row by a constant, then the determinant of B is K times the determinant of A. So you multiply, so the new determinant is K times the old determinant. This is very, very important. This is the new one. This is the old one. I'm going to say more words about this in a second, and I'll give you a shortcut. But the star of the show, absolutely the star of the show is this. If you add a multiple of a row to another, the determinant does not change. And this is the one that we absolutely love. If we add a multiple of a row to another. Now, let me ask you this. We haven't done this in this session, but we did it in the session for midterm 2 if you were there. What do we usually use this operation to get? When we add a multiple of a row to another, we're doing this to get what? Well, we're doing it to get zeros, no? When we use like minus 3 row 1 plus row 2, are we using that to get zeros, to get into RREF? And isn't this amazing? So I can create a bunch of zeros in my matrix without ever changing the determinant. And the more zeros we have, the faster cofactor expansion is. Okay. Let me show you how this is done. Let's say you want to find the determinant of the matrix. I'm going to get a big matrix here. 4, 2, minus 1, 1. You should know that they even give you bigger than this. In 2020, they gave you a 5 by 5 matrix. I don't know why I'm just copying this particular matrix, but we could do any matrix. Look, you're not talking to me, but I hope that you're talking amongst yourselves, right? So you can just answer this. What is your optimal scenario? And don't say the zero matrix. Obviously, like if it was Christmas in April, then they give us the zero matrix and say the determinant, and the answer is 0, and we live happily ever after. That's not going to happen, all right? So what's the realistic best case scenario? The more zeros you have, the easier the cofactor expansion is. So imagine this was 0 and this was 0. Then all you need to do is just do the cofactor on this column, and all you need to worry about is one entry. Do you see what I'm saying? Like the best case scenario is a column full of zeros. But we can achieve a column full of zeros by adding a multiple of a row to another. We are trained to do this. This is how we get the solution to systems, right? So you pick a column. I mean, it's not nice to pick on people, but you can pick on columns. So pick a column and then decide to get as many zeros as possible in that column. For example, there's a 0 here already done. So you can keep that one and use it to get a 0 over here and a 0 over here. And this operation does not change the determinant. So if you do minus 2 row 2 added to row 1 into row 1, the determinant doesn't change. And if I do 2 row 2 plus row 4 into row 4, the determinant doesn't change. So I can still say equal determinant of. Do you understand why we love this now? Because it's an operation that gives us zeros at no cost. So this row doesn't change. This row already had the 0 in it. So minus 2 this plus this, minus 2 this plus this, minus 2 this plus this, minus 2 this plus this. 2 this plus this, 2 this plus this, 2 this plus this, and 2 this plus this. We got a whole bunch of zeros. And look, you guys, you can decide now conveniently to expand, to use cofactor expansion along column 2. So you do your signs, plus, minus. So this is minus, plus, minus, plus. And realistically, all you care about is this entry. Everything else is 0. So it's plus 1 times the determinant of, cancel the row and the column. You get 0, minus 5, minus 1, 3, 1, 1, 5, 3, 0. Now you can decide to just do cofactor expansion right away. You don't need to recreate more zeros. But if you really love this method, you could do it again. You can say, okay, which column I'm going to cancel? Look, here I have a 1. I like it. So here's a 1. I'm going to cancel this. I mean, it's a 3 by 3. So usually we just do it right away. We don't reduce anymore. But for fun, let's reduce this. So we're going to do the operation row 2 added to row 3 into row 3 to get the 0 here. This operation has no cost. So we can say the equal determinant and plus 1 times, that's just the same thing. So this row does not change. This row does not change. So this plus this plus this, and this plus this. And you can magically decide to expand along column 3. Magically, right? You're setting this up. So you get your sign matrix, plus, minus, plus, minus, plus. So we don't care about those. And realistically, all you care about is this entry. So minus, entry, determinant, cancel row and column. You get 3, minus 4, 5, 3. And you're set. So this would be minus 9 plus 20. So the answer is minus 29. This is very, very, very fast. Right? This is incredibly fast. Do we get this? Of course, do check all my calculations, please, if I've made a mistake. So very simple. We use row reduction to get a column that's full of zeros, and then we expand them on that column, and we live happily ever after. Now, here's a very important note, and then I'm gonna do another problem to illustrate that note. In determinants, in finding determinants, we are allowed to factor a number from a row or a column. Of course, in determinants, not in any matrices. So for example, if I tell you what's the determinant of, and I say 2, 2, 3, 5, see, you don't need to here, but I'm illustrating the rule. You're allowed to factor 2 out of row 1. You can pull 2 out of row 1 and say this is 2 times 1, 1, 3, 5. It seems useless here, but believe me, it's not useless. It's a very useful operation. So this is 2 times 5 minus 3. So this is 4. Okay. Let's go to 2020. APSC 2020. They did ask them a huge determinant. Use at least to compute the determinant of B and C. So pick one. Would you like B or C? I'm guessing you would like C, but C is not so bad. B or C? Well, you're not saying anything, so I'm going to go with the bigger one, C. So in 2020, you got asked to find the determinant of C. So the determinant of C equals to. Do you want to tell me how to proceed? Well, clearly column 4, right? Column 4 is made up for me. It's made of all zeros except the 7. So if I look for my signs, plus, minus, and then plus, minus, plus, minus. So again, I only care about the 7. So minus 7, the determinant of, and now cancel this and cancel this. That'll give me 3, 2, 0, 6, 3, 3, 0, 6. Wow, those are nice. 2, 12, 3, 3, 2, 6, 3, 1. So how do I continue? See, you look at column 3 and you realize you could easily just do minus this plus this or minus this plus this and get a 0. Can we see that? So if I look in column 3, I can use this entry to cancel this entry. So, and this is at no cost. So I could do, there's the operation is minus row 3 added to row 4 into row 4. This operation is at no cost because it's adding a multiple of a row to another. So minus 7, and then the determinant of, you know what, just allow me to copy it. And now I'm just going to cancel this. So minus this plus this, minus this plus this, minus this plus this, and minus this plus this. And now I conveniently expand along column 3. Here I should have said column 4. So plus, minus, plus, minus, plus, minus. And I only care about the 3 because the rest are zeros. So there's that minus 7 that I keep carrying. Now I have plus 3, so that's 3, the determinant of the matrix. I cancel this and I cancel this. So 3, 2, 6, 3, 3, 6, 0, minus 6, minus 2. Notice how I'm dropping this super fast from 6 to from 5 to 4 to 3 and now to 2. Okay, what I wanted to mention is you can use this 3 to cancel this 3, but you can also, if you decided, you are allowed to, let's say, factor a 3 out of this column. You don't need to do here because you can just do minus row 1 plus row 2. But if you wanted to, you could factor out, let's say, a 3 out of this column. If you wanted, you could say this is minus 7 times 3 and factor out a 3 from column 1, and you'd get the determinant of, I'm going to write it down in red, 1, 1, 0. You know what? Let's do those in black. So minus 7 times 3, and then the rest is the same. 2, 3, minus 6, 6, 6, minus 2. You can factor out a number from a row or from a column. You don't need to, because here the 3 would have canceled the 3 anyway, but I wanted to express it. It's not in this case, Johnny, it isn't like you don't need it. But let's say you have this matrix where you have, let's say, 2, 14, and then 8, and then like whatever, 3, 7, 15, minus 2, 4, 8, right? Let's say you want to find the determinant. There's no ones, right? There's no ones. And let's say that, you know, this was 4 and this was 7, let's say. So You can't cancel, and let's make this 9. Right? You want to get a leading one so you can get zeros in your columns, but there's no way to get a leading one anywhere. This doesn't cancel those, this doesn't cancel those, this doesn't cancel those. So how do you cancel things? You realize, for example, that you could have factored 2 out of row 1. So you factor out a 2 out of row 1, and then you say determinant. Of course, don't say I'm factoring a 2 out of row 1. This is not the real operation. This is what the operation looks like. And you are allowed to do this. And now you can use that one to get zeros over here. And your matrix, your determinant is easier to find. Do you get what I'm saying? In fact, I'm just going to leave this as a no. You see what I'm saying? Now you're able to get a 1, and then you proceed like this. The real operation, if you must know, and I really don't want to spend a lot of time on it because I just want you to be able to solve the questions. We're not going to do a lot of theory here. The real operation is a half row 1 into row 1. But when you do the half row 1 into row 1, the half is here. Because look, when you look at the operations, it's the half, what you multiply by the row is multiplying the old matrix. So the K, the half that you did, would appear next to the old matrix. So this is the old matrix, this is the new matrix. So when you bring the half to the other side, it shows up as 2. But this is complicated, so we just think of it as factoring a row out of a column. You can write the operation if you want to fake it really well, but don't use it. Think about it as you're factoring a row out of a column or out of a row. Is this clear? So now I could do minus row 1 plus row 2 into row 2. Of course, I could have done that earlier. It would have canceled here, but I wanted to stress this fact. So this is minus 7 times 9, so minus 63. The determinant of 1, 2, 6, minus this plus this, minus this plus this, minus this plus this, and then this is 0, minus 6, minus 2. Now I have the option of column 1 or row 2, or I have the option of doing, if you want also, you can say here 3, no, you can't do that. It wouldn't work. You can do 6 row 2 plus row 3 into row 3. This operation, if you want, of course, you can, from here, you can expand on column 1 or row 2, or if you really want to do the other method that we did before, you can do 6 row 2 plus row 3 into row 3. So that gives you minus 63, 1, 2, 6, 0, 1, 0, 0, 0, minus 2. And what do you get? You get a matrix that is upper triangular. So you can get an upper triangular matrix, and therefore this gives you minus 63 times 1 times 1 times minus 2, which is 126. Again, or you could do this or this. I'm just showing you different options. So you could have expanded on column 1, where you would have gotten minus 63 times 1 times the determinant of 1, 0, minus 6, minus 2, which would have been minus 63 times minus 2, which is 126. Obviously, the same answer. I'm going to pause for a second. Do you understand what just happened? So this is how we find the determinant of a matrix in the most efficient way. We combine row operations with expanding with the cofactor expansion, and that reduces our matrix greatly till we get either we transform it into an upper triangular matrix, or we just keep going until we get a 2 by 2 determinant, and that's easy to find. Questions, comments, movie reviews, anything at all? Everything's okay? Can I move on to a new topic? Harry, you usually tell me everything's okay, so I trust you and everyone, but I mean, so can I move on to something else? I'm going to assume you said yes and move on to the properties of determinants. So properties of the determinant function. Remember that determinants are only of square matrices, so they are of matrices that are n by n, right? So the properties goes as follows. That's good. Oh, very good. Very good. We like it. So, first of all, determinant, and this is a huge, huge property. The determinant of a matrix times another matrix is the determinant of A times the determinant of B. So the determinant of a product is the product of determinants. What follows from this is if you take the determinant of a matrix A to the power k, this would be the determinant of A times A times A times A times A k times. That would be the determinant of A all raised to the power k. So for example, if you take the determinant of A to the power 3, that's like taking the determinant of A and raising all of it to the power 3. Now, if you take the determinant of a constant times the matrix A, so if you want to bring out a constant out of the determinant, it comes out as constant to the size of n, to the size of the matrix, times determinant of A. Please, this is not the same thing as we were doing before. Here, I was taking a 2 out of row 1. I wasn't taking out a 2 out of the whole matrix. I was taking a 2 out of only one row. Here, this operation is taking a k out of the whole matrix. So the k out of row 1, k out of row 2, k out of row 3, until k out of row n. This is why we have k to the power n, because there is a k coming out of every row. So the determinant of A transpose, this is, by the way, called A transpose. Let me explain what the transpose is. Suppose we could have done matrices before this. Maybe next time I do this, I do matrices before. So what is the definition of A transpose? What's the definition of A transpose? Do you know? This is A transpose. This is the matrix whose rows are the columns of A, and of course, and vice versa. So the rows become columns and the columns become rows. So for example, if A is equal to A, B, C, D, then A transpose becomes, the rows become columns. So A, B, C, D. And the determinant of the transpose is the same thing as the determinant of A. So when you transpose a matrix, it has no effect on the determinant. And finally, a very important property, the determinant of the inverse. This is A inverse, and I'm going to dedicate a whole lot of time to discuss inverse with you. The determinant of the inverse is 1 over the determinant of A. Now you're going to tell me, wait, what if the determinant of A is 0? But A can't be 0. The determinant of A cannot be 0 because of this very, very, very important theorem that says A inverse exists, so the inverse exists. That is equivalent to saying that the determinant of A is not 0. I'm going to dedicate so much time today and tomorrow to talking about this idea and what it entails theoretically. So A inverse exists means A has an inverse, and we're going to say more about the inverse in just a bit if the determinant of A is not 0. So let me show you what kind of questions, for example, they would say. So let's pick 2018. That's eigenvalues and eigenvectors. We're going to do this in a bit. I thought there was a question. Am I crazy? I wrote here, look at 2018. Here we go. That's it. So here is A. This is from 2018. What should A, the question is, here's A. For what A is A invertible? For what A is this matrix invertible? Please, 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 let's agree on this. Is very important. Invertible means that A inverse exists. It means A has an inverse, whatever that means for now. I will explain it to you in a second. And the very important theorem tells us that a matrix has an inverse if the determinant of that matrix is not equal to 0. You don't need to understand why, but you need to understand that invertible, the inverse exists if the determinant isn't 0. So I'm going to give you 10 seconds. What's the determinant of A? You don't even need 10 seconds for this. What's the determinant of A? Look, you guys, this is a matrix that is lower triangular. Everything above the diagonal is 0. So the determinant of A is 1 times A plus 1 times 1, which is basically A plus 1. And you want the determinant not to be 0, so A should not equal to -1. Right? Let me ask you another question. Let's say we have a matrix A that's 3 by 3, and the determinant of A is equal to -2. So tell me, what is the determinant of 2A transpose? And tell me, what's the determinant of 3A inverse? Okay, take 30 seconds, please. And the answer is so if you take out a 2 out of the determinant, it will come out as 2 to the power size of the matrix times the determinant of A transpose. Now we know that A transpose doesn't affect the determinant. Determinant of the transpose is determinant of A. So this is 2 to the power 3 times the determinant of A, which is 8 times minus 2, which is minus 16. Okay, how would the determinant of 3A inverse equal to? So we pull the 3 out of the determinant. That comes out as 3 to the power 3, determinant of A inverse. So this is 27, and we know that the determinant of A inverse is 1 over the determinant of A. So this is 27 over minus 2, or minus 27 over. I can. Do you remember the property that says the determinant of a constant times the matrix A? If you want to take the constant out of the determinant, you raise the constant to the size of the matrix, and then you say times determinant of A. This is one of the properties. So if you want to take the 2 out, it's going to come out 2 to the size of the matrix. 2 is K, times the determinant of the transpose. But the determinant of the transpose is the same thing as the determinant of A. When you transpose a matrix, you don't change its determinant. So the determinant of the transpose is the determinant of A, and the determinant of A is minus 2. Same story here. When you take the 3 out of the determinant, it would come 3 to the size of the matrix. Then you're left with the determinant of A inverse. The determinant of A inverse, as the property would say, is 1 over the determinant of A. So instead of determinant of A inverse, I wrote 1 over the determinant of A. And I know what the determinant of A is. So this is 27 times 1 over minus 2, which is minus 27 over 2. Excuse me. Do you get this? Only for n by n matrices. The whole concept of determinants, Johnny, is for n by n matrix. There is no determinants for matrices that are not n by n. Right? When we started this, we said determinants of a matrix that's n by n. So if a matrix isn't n by n, then a matrix doesn't have a determinant. Here's another question. Let's say A is 2 by 2, B is 2 by 2. The determinant of A, by the way, determinant of A, sometimes some books write it absolute of A. It's a way of writing it. If you want, you can write it like this. If you don't want, then don't write it like this. The determinant of A is minus 1, and the determinant of B is minus 2. What is the determinant of 3A, B, A, B, A, B? And next, what's the determinant of 2 A inverse A transpose B, B squared, A, B transpose. Let's put B inverse. Well, look, it all is in this property. The determinant of a product is the product of determinants. So this is, first we're going to take the number out. So this is going to come out 3 to the power size. Then determinant of A, determinant of B, determinant of A, determinant of B, determinant of A, determinant of A, determinant of B. The determinant of a product is the product of determinants. And now each one of those is just a number. So this is 9 times this, times this, times this, times this. Those are numbers. So this is the determinant of A to the power 4. And this times this times this. This is the determinant of B to the power 3. So this is 9 times minus 1 to the 4 times minus 2 to the 3, which is 9 times minus 8, which is minus 72. This got asked on a test once, but on a final, this got asked. And I decided to give you this one, which is the same version of this, but only more fun. So can you try and find this? I'm going to stop talking for a minute. Please try finding this. And if you have questions, I'm right here. Okay, as a first step, what happens when you bring the 2 out? It's going to come out as 2 to the power size of the matrix. Now you have this times this times this times this times this. So you're going to do the determinant of each. You can write them in absolute value, or you could just write them as determinant. So this is determinant of A inverse, determinant of A transpose, determinant of B, determinant of B squared, determinant of A, determinant of B inverse. Do you get this step? So now you know how to do each one of those. The determinant of A inverse is 1 over the determinant of A. The determinant of A transpose is the same thing as the determinant of A. The determinant of B is minus 2. The determinant of B squared is the determinant of B all squared. The determinant of A is minus 1. The determinant of B inverse is 1 over the determinant of B. So let's simplify. Minus 1 times minus 1 is plus 1. Minus 2 divided by minus 2 is gone. So that would be minus 4 times 4, and the answer is minus 60. Do we get this? And that, ladies and gentlemen, is how we find determinants. Now we are going to use determinants to find eigenvalues and eigenvectors. But first, I want to just go and discuss matrices with you. So the next step, if you don't have questions, of course, I'm going to go to here and we're going to discuss matrices. So what, most of the stuff we did already, but I want to focus on specifically matrix multiplication and finding the inverse of a square matrix. So if you don't have any break, I guess, how do you know the determinant of B is -2? It's right here. Johnny, this means this is an abbreviation to say determinant of B. When you put absolute value on a matrix, right, that means the determinant. It's a notation. So it was given to us as the determinant of B is -2. Right, so this, when you say absolute value of M, that means the determinant of M for matrix M. Any other questions? Why I squared this 3? By all means, Harry. Do you remember the property that says if you have the determinant of K times the matrix A, when you want to take the number out of a determinant, of a whole determinant, you take A and you raise it to the size of A times the determinant of A. This comes from the size of A, and A is 2 by 2. So that 2 is that 2. Or B, because they're all the same. And that 2 is also that 2. Do you have any other questions? It's n by n, my dear Harry, right? Like a matrix A is n by n. It's the same thing whether you pick the first or the second, because determinants only happen with square matrices that are square. So there is no determinant of a matrix that is not square. So if A was 3 by 2, you couldn't find the determinant of A. Determinants are only for square matrices. Harry, I am the one that thank you. Thank you for talking. Thank you. Anyone who asks a question, I am the one that thanks them, because questions make the session more interesting. Anything else? All right, so we've reached our first break. Right now it is 6:46. Let's just take 15 minutes and let's be back at 7:01. If we need to, we will make the next break a little bit longer. And then when we come back, we're going to do matrix multiplication and certainly matrix inverse, so we can proceed to do systems and then eigenvalues and eigenvectors. All right, see you guys in a bit. And if you need to email me questions, you know my email. Hey everyone, we're back. So let's talk matrices. So we know that a matrix is a box of numbers. A matrix in general, A, is a just box of numbers. It would have size m by n. Excuse me. This is a general matrix. So it would have m rows and n columns. Of course, if a matrix is square, then it's n by n. So we call the identity matrix. We talked about this earlier. The identity matrix is the matrix I, where it's ones on the main diagonal and zeros everywhere else. So for example, identity that's 2 by 2 is 1, 0, 0, 1. The identity that's 3 by 3 is 1, 0, 0, 0, 1, 0, 0, 0, 1, and so on. And why do we care about the identity? We're going to learn about matrix multiplication in 30 seconds. We care about the identity because I acts like 1 in matrix multiplication. So the identity I times any matrix A will give me A times the identity I will give me the matrix A. I raised to any power you want, like I times I, that would give me I. So literally, it's the one of matrix multiplication. Now, let's discuss what is matrix multiplication. First of all, to be able to multiply matrices, when we have a matrix A that is m by n, we need to multiply it by a matrix B that is n by p. For matrix multiplication to be defined, n and n should be the same. And the answer is going to be, so the matrix that we get, the final AB, the size of the matrix we get is going to be m by p. So this m by p is going to be the answer matrix. So that's the first hurdle in matrix multiplication. You need the n's to match, and the answer is m by p. Now, how do we actually do matrix multiplication? Let me give you an example. So let's say I have a matrix A. I don't want to call them anything. I'm just going to write the matrix. So let's say the matrix is 1, 2, minus 3, 1, 3, 4. This is a matrix that has 3 rows, 2 columns. I'm multiplying it by a matrix 1, 3, minus 1, minus 2. So I'm multiplying it by a matrix that is 2 rows, 2 columns. Let's agree that this matches this, so that multiplication is valid. The answer matrix is going to be 3 by 2. So the answer matrix is going to be 3 by 2. So we're going to get a matrix that has 3 rows, 2 columns. So 1, 2, 3, 4, 5, 6. Please pay attention. How do we find the entry here? This entry that is in row 1, column 1. So to do this, you take row 1 and column 1, and you multiply them out. You do their dot product, or you just you don't need to call it anything. Just do their multiplication. So 1 times 1, you multiply them, and then you add 2 times minus 1. So that would be 1 minus 2, which is minus 1. Okay, what would be the one here? This is the entry here that's in row 1, column 2. Look, it's in row 1, column 2. So what you do is you take row 1 with column 2, and you do the same idea, right? So you go through a row, and then you go through a column, and then you multiply and add. So This would be 1 times 3 plus 2 times minus 2, which would give me minus 1 also. Let's say this one. This is the entry in row 2, column 1. So you take row 2, column 1. Same trick. You go through the row, you go through the column. That's minus 3 times 1 plus 1 times minus 1, which is minus 4. This one is row 2, column 2. So I'm going to take row 2 with column 2. That would be minus 3 times 3 plus 1 times minus 2, which is minus 11. This one is row 3, column 1. So I'm going to go to row 3, column 1. This is 3 times 1 plus 4 times minus 1, which is minus 1. And finally, this one is row 3, column 2, which gives us 3 times 3 plus 4 times minus 2, which is 1. That's how we do matrix multiplication. Of course, given that these two are the same, if these two were not the same, then matrix multiplication would not be defined. So for example, if you take a matrix A that's 3 by 2, and you have a matrix B that is 4 by 3, then A times B is not defined. You can't multiply A by B because they don't have this, doesn't match this. While on the other hand, you could do B times A. B times A is defined, and it has size 4 by 2. Because B is 4 by 3, A is 3 by 2, they match, so the final size is 4 by 2, and you can do it. Okay, so what does that tell us about matrix multiplication, guys? What does that tell us about matrix multiplication? It tells us that, and this is important, this is a very important note. It tells us that matrix multiplication is not commutative. This is very, very important. A times B is not equal to B times A. So A times B is not equal to B times A. Also on the side, I want you to know that matrix multiplication is side sensitive, meaning if you have A equals to B and you want to multiply by matrix C, you have to multiply on the same side. So you have to say AC equals to BC, or you can say CA equals to CB. You cannot say CA equals to BC, because you multiplied by C on the left here, you multiplied by C on the right here. That's not allowed. Right? Okay, some very, very important notes about linear combinations. So I'm gonna link matrix multiplication to linear combination, matrix multiplication and linear combination. When you multiply a matrix by a vector, when you take a matrix A and you multiply it by a vector V, you are creating is a linear combination, is a linear combination of the columns of A. Let me show you. If you take the matrix A, let's say 1, 2, 3, 4, and you multiply it by the vector xy, Please pay attention because this is important. This is a 2 by 2 matrix. This is a 2 by 1 matrix. A vector is also a matrix. It's 2 by 1. So how can I write this as a combination? Please pay attention. It's as if we're saying X times column 1 of A plus Y times column 2 of A. So you can see that this is a linear combination of the columns of A, which means that this is in the span of the columns of A, right? Since it's a linear combination of the columns, and that means it's in the span of the columns of A. And what's another name for the span of the columns of A? This is called the image of A. Naturally, A times V is in the image of A, right? That's the definition of the image of A. Image of A, by the way, is all the vectors W such that W is A times V, such that all the vectors W that are A times a vector V. So clearly AV, if you call it W, it's in the image of A because it's A times some vector V. Excuse me. In general, if I have a matrix A that is M by N, I am multiplying it by a vector V that's N by 1. N by 1, by the way, this means in Rn because it has N components. So if we have a matrix A that's multiplied by a vector x1, x2 up to xn, remember, multiplying by a vector, that's like creating linear combinations of the columns. So this is like saying x1 times column 1 of A plus x2 times column 2 of A plus all the way till you get to xn times column n of A. Right? So that's an important note about the columns. So this means this is in the span of the columns of A. Because literally it's a linear combination of the columns, because this is a linear combination of the columns of A. Right, now let's talk about what an invertible matrix is. So what is an invertible? What are invertible matrices? What is the inverse of a matrix A? So inverse, like determinant, is only for square matrices. We do not talk about the inverse if the matrix is not squared. So the inverse of matrix A, that's n by n, if it exists, we have no guarantee that a matrix has an inverse. If it exists, is the matrix such that is the matrix A with a -1, which we read not A to the -1, we read A inverse, such that, what's the definition of the inverse? It's the matrix that you multiply by A to get the identity. See, or you can do it like this, or you can do A times A inverse equals to the identity. In the case of the inverse, it doesn't matter on which side you put it. So what's the inverse of a matrix A? The inverse of a matrix A is the matrix that you multiply it by to get the identity. So the inverse, I'm going to write it in English. The inverse of A is the matrix you multiply by A to get the identity. And that is extremely useful in linear algebra. So we know what the inverse is. How do we find it? So how do we find A inverse? Next topic is finding A inverse. Finding Nemo. So how do you find A inverse? There's a formula for 2 by 2. I encourage you to know it, but you don't actually need to know it. You can use the general method that's for n by n. So for 2 by 2, I'm going to give you a formula, but then there's a method that works for any n by n. I will show you both methods. For a 2 by 2, the formula is simple. If you have A equals to A, B, C, D, then A inverse is equal to 1 over the determinant of A, so AD minus BC. We know this to be the determinant of A times the matrix, where you change the places of D and A, and you change the places, you change the sign of B. So you can write this as 1 over the determinant of A times D minus B minus CA. Now, what am I going to say now? I'm going to focus now on the fact that I'm dividing by the determinant of A, on the fact that I stressed a lot when we were talking earlier, the fact that if the determinant of A is equal to 0, then I'm dividing by 0 and there is no inverse. Right? This is very, very, very important for all sizes. A inverse exists, meaning this means that A has, actually, this is a silly explanation. A has an inverse if and only if the determinant of A is not equal to 0. Very, very important item. And this is for any size A. Great. So let me give you an example. So for example, if A is equal to 1, 2, 3, 4, let's say. So A inverse would be 1 over 4 minus 6, the determinant. We switch the sides, we switch the places, and we multiply. We change the sign. So 1 over minus 2. So this is going to be minus 2, 1, 3 halves, minus 1. And you can check. Oh, we're going to get to what it's used to. Unfortunately, in this course, Johnny, you don't use it for much. And unfortunately, in 174, there's not a lot of applications you use the inverse for. But in all fairness, the inverse is one of the most important things you learn in a linear algebra course. Like it's very, very important. Unfortunately, again, in 174, you barely do any application. Like, what do you use the kernel for? Right? What do you use the image space for? What do you use the determinant for? Like none of what you learn in APSC 74 you actually apply. The only application I've seen is the tanks problems, right? You have the tanks problems, you've seen the tanks problem. So that's the only application that we've seen in this. But trust me when I tell you, this has a billion applications. So you can check if you want here. You can check if you want that when you take A and you multiply it by A inverse, you are guaranteed to get the identity 1001. Okay, so what is the method to find the inverse? If it's not 2 by 2, if it's any n by n, see, here's how you do it. You write A and you put the identity next to it. Then you row reduce. You row reduce, meaning you aim for RREF. Once you get I on this side, what you get on this side, that will be the inverse. Now, there's a reason for this, but they don't ask you to prove it, so it's fine. So, when you reach I, meaning the reduced row echelon form of A is I. We did reduced row echelon form in midterm 2. I will remind you what this is. What is reduced row echelon form? RREF. We did this in, again, midterm 2, but I will remind you of it. So this is the final stage that we get to, the final the final matrix. This is in RREF when we stop. This is if, I wonder if I can copy it from somewhere. Too bad. So if all 0 rows are at the bottom, all 0 rows are at the bottom. Of course, if any, you don't necessarily have 0 rows. The first non-zero entry of a non-zero row is a 1. That's what we call the leading one. Leading ones go left to right. And finally, above and below. Below we have it for free, but above, all leading ones, the entries are 0. So above and below leading ones, the entries are 0. This is when we say we've achieved the reduced row echelon form of a matrix, when it satisfies these conditions. Great, let's pick an example. In 2020, I'm sure they asked this. Determinant. Here we go. See, this is what they asked in 2020. And then, Jason, I can show you how it can be used to solve a system. So one way to use the inverse is maybe to solve a system. It's a very, very not fast way. It's a very, slow and expensive in terms of time way, but I'll show it to you. So how do you find the inverse of this matrix? Use the RREF algorithm. So reduce to find the inverse. How do we do this? Right? How do we do this? I explained this to you. So you put A 3 1 5 4 0 5 0 1 1, and then 1, you put the identity next to it, 1 0 0 0 0 1 0 0 0 1, and you want to reduce until you reach RREF. Like you want to reduce until you get to RREF. Okay, so we've worked on this in midterm 2. I'm gonna repeat the strategy. We're gonna work column by column. I will rewrite the strategy here, even though we did this in midterm 2, and even though this is in the pre-recorded part. So this is all explained in the part of the session that I recorded for you, but I will say it again. We work column by column. And in a column, we first get the 1, the leading one, of course, and then we use the 1 to get zeros. That's our strategy. So I need a 1 over here. The easiest way to get 1 over here, the one that doesn't require any brain power, is take row 1 and divide it by 3. Of course, there's an easier way, but you would have to see it. You can do minus this plus this. So it becomes a -1. So then you multiply it by -1. Or you can do, if you don't want to do this and get fractions, you can do minus row 1 plus row 2 into row 2. You take this and you minus it from this. That gives you in row 2, 1, -1, 0, -1, 1, 0. So this row isn't changed. And now you switch these two rows. So you create the 1 in the bottom row. Then you can say, okay, now I'm going to switch row 1 and row 2. And that'll give me the 1 that I wanted. Okay, listen, you could have done it using dividing row 1 by 3. The only disadvantage to dividing row 1 by 3 would have been that you will deal with fractions. But you're not scared of fractions. I don't think so. So now I need a 0 over here. So -3 row 1 added to row 2 into row 2. 1 -1 0 -1 1 0. This row doesn't change, so I'm just going to keep it. So -3 this plus this, 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 and this. I'm done working in the first column. Now I need the 1 over here. Well, I could easily switch row 2 and row 3. That wouldn't mess up my zeros here. And that'll give me a free 1 without actually doing any fractions. 0, 4, 5, 4 -3, 0, 0, 1, 1, 0, 0, 1, 1 -1, 0, -1, 1, 0. So I got the 1 where I need it to be. Now I'm going to use it to get a 0 here and a 0 here. So row 2 as is added to row 1 into row 1. That gives me the 0 here. And -4 times row 2 plus row 3 into row 3. So what does that give me? Let's do this. This row isn't changed. 0, 1, 1, 0, 0, 1. So let's add row 2 and row 1. So this will give me 1, 0, 1, -1, 1, 1. And -4 this plus this, -4 this plus this, -4 this plus this, -4 this plus this, and -4 this plus this. Look at that. I got a 1 where I need it with no effort. So I'm going to use it to get 0, 0, and 0, 0. So minus row 3 added to row 2 into row 2. And minus row 3 added to row 1 into row 1. These operations are like crazy apt. You miss a minus, you forget a 1, you copy a value wrong. So please be careful when you do these operations. So minus this plus this, 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 and minus this plus this. And ladies and gentlemen, boys and girls, this is your A inverse. When you reach the identity on this side, you have the inverse on the other side. That's how the inverse algorithm works. Now, they're telling us, look, I'm going to show you this. Even though we haven't done systems today, but we have done systems in midterm 2, and I have done systems in the on-demand part, or the part that is posted for you. How could you solve this system? I mean, you can solve it using the regular way, right? You can we all agree you can solve this in the most regular way. But how could you solve this system if you wanted to use the inverse? So option number 1 to solve, write the augmented matrix and reduce. Now you could always do this, but option number 2 is more interesting here because I already have A inverse. Let me show you something. Please pay attention. This system, in fact, any system of linear equations, can be written as coefficient matrix times variables equals right-hand side. A is the coefficients, X is the vector of variables, and B is the right-hand side. So this system that you see in front of you, we can write it as 3, 1, 5, 4, 0, 5, 0, 1, 1 times X, Y, Z, those are the variables, equals to 2 minus 3, 4. Where if you look closely enough, this is matrix A. This is the matrix A that we had here. Great. So I have A times X is equal to B. How do I solve for X? Remember, these are matrices, so there is no matrix division, right? We don't know of matrix division. How would you solve for X? And this, Jason, is one way that one can use the inverse. This is one way where the inverse is very useful. You have AX equals to B. What you do is you multiply by the inverse on this side, and you multiply by the inverse on this side. Remember, it has to be on the same side. Look how useful this is. What is A inverse times A? Ladies and gentlemen, boys and girls, what is A inverse times A? What does A inverse times A give us? It gives us the identity. That's the whole point of the inverse. So the identity times X is A inverse B. The identity times X, that's just like X, because identity is like 1. So to find X, all you need to do is take A inverse and multiply it by B. So you pick up A inverse from here. And you multiply it by B. I remind you, B is the right-hand side, 2 minus 3, 4. And that gives you your solution. So you can do this as a linear combination of the columns if you want. This is 2 times minus 5 minus 4, 4. Minus 3 times 4, 3 minus 3. Plus 4 times 5, 5 minus 4. Or, of course, or regular multiplication. The one we did it before. So this would be minus 10, minus 12, plus 20. This would be minus 8 minus 9 plus 20. And this would be 8 plus 9 minus 16, which gives us the vector minus 2, 3, and then 8 plus 9 minus 16 as well. So basically, x, this is the vector x, y, z. So x is minus 2, y is 3, z is 1. You ask me what the inverse can be used for, and the inverse can be used for this. Is it a very good use of the inverse? No, it's not. There are other way more important uses for the inverse, and this is definitely, I mean, it's a way to use the inverse, but it's not the why we use the inverse. The inverse is much more important than just to solve a system of linear equations. So what did we learn so far? We learned that a matrix is invertible if its determinant is not 0. We learned that when we multiply a matrix by its inverse, we get the identity. And we learned that we can get a solution to a system if we multiply the inverse by the right-hand side using this rule right here. Right? Now, I'm just gonna say a quick reminder about systems of linear equations. So reminder about systems of linear equations, because those were done in part 2, and those are done in systems of linear equations. Right, see, those are done in the part that I've recorded for you, and the session is available to you already. You can check it. And we did row reduction, we did RREF, we did all of that. So I don't want to redo like things twice. It makes no sense. I'd be wasting your time. But I'll do a quick reminder. How would you solve a system? So let's say in 2020 they asked a nice question. If I can just get it. Here we go. So let's say you are being asked to solve, and this was a different type of question than what I want, but here we go. So how would you solve this? Let's just erase. So let's say somebody is asking you to solve this system. So solve this. Right? To solve this system of linear equations, so this would be the augmented matrix, right? So this is the augmented matrix. So this is the matrix where these are the coefficients of x, this is the coefficients of y, this is the coefficients of z, this is the coefficients of w, and this is the right-hand side, or we can use x1, x2, x3, x4. Now, we reduce the system, we talked about reducing it, we get to this. So how do we solve, how do we write the solution to the system of linear equations? Okay, let's remember, the variables that do not get a leading one get a parameter. So x got a leading one, y got a leading one, z did not get a leading one, w got a leading one. So z becomes a parameter, becomes a free variable. Now let's solve. This line tells me that w is simply equal to 1. This line tells me that y is equal to -4 plus 3t. And this line tells me that x is equal to 3 minus 4z, so minus 40. So my solution to this exercise, remember we write it as a vector, x, y, z, w. It's a vector of constants plus a vector times t. So 3 minus 4t, minus 4, 3t, 0 and 1t, and 1 and no t. I'm going to ask you another one, just so we can make sure that we're on the same page and you understand how do we solve systems of linear equations. So let's say this. I'm going to make this difficult, okay? I'm making this spicy. So how would you solve this? 0, 1, minus 1, 0, 1. Let's say with 3. And then 0, 0, 0, 1, 2, 5. And let's all give the same names to our variables, x1, x2, x3, x4, and x5. How do you write the solution to the system of linear equations after you reduce it to this? I'll give you one more minute. So x did not get a leading one. x2 got a leading one. x3 didn't. x4 got a leading one. So x1 will be s. x3 will be t. x5 will be r. Let's see. So what is x4? This line will give us x4. It's 5 minus 2x4 minus 2x5, which is minus 2r. This line will give us x2. It's 3 plus x3 minus x5. No, careful, Johnny. You look at them like this, not like this, right? In this row, the first entry that's not a 0 is here, and that's the leading one. In this row, the first entry that's not a 0 is 1, and that's the leading one. This is not a leading one. Look, there's many things that come before it, right? Only those two are keywords, leading one. Did you get what I'm saying? Those are leading ones. So the first entry that's not a 0. So how do I write this as a vector solution? So constants plus a vector for s, a vector for t, and a vector for r. So there's a lot of vectors there. So, and this is x1, x2, x3, x4, and x5. So x1 is 0 everywhere, just one s. x2 is 3, no s, 1t minus 1r. x3 is zeros everywhere except 1 for t. x5 is 5, no s, no t minus 2r. x4, sorry, and x5 is 0, 0, 0, 1 for r. By the way, tell me something. This matrix is in RREF. We reduce it to RREF. What is the rank of this matrix? out of curiosity, do you remember what rank means? The rank is the number of leading ones, so the rank is 2. So the rank is the number of leading ones in RREF. Just so you know. Okay, now I'm gonna mention a very important theorem. Please, please, please pay attention. I said this a few times and I'm gonna say it again. Look, let's say that A, n by n, is invertible. Invertible means it has an inverse. It means A inverse exists. Okay, tell me something. What is this equivalent to? If the inverse exists, that means I can start with A, put the identity next to it, and then I can reduce, and then the identity will appear here, and the inverse will appear here. This is the process of finding the inverse. So when I say my matrix is invertible, I mean it's possible to do this. What is this equivalent to? This is equivalent to the determinant of A not being 0. We talked about this. More importantly, this is equivalent to the reduced row echelon form of A is the identity. Super important. It means I am able to go from A to the identity. This is very, very, very important. That means the rank of A is n, because it's the identity. That means it has n leading ones. Now, I don't know if you remember what we did in the session for midterm 2, but what is the rank of A? This is a very important quantity. What is the rank of A? This is a very, very, very important quantity. When we prepared for midterm 2, we said it. The rank of A, that's the dimension of the image space of A. This is very, very, very important. So that means, I mean, midterm 2 or not, this is important. The rank of A is the dimension of the image space of A. And we said that in this case, A is n by n. So if A represents a transformation, it will be from Rn to Rn, right? Remember, I drew this arrow in the session, n by n. We're gonna do linear transformations later today, but I'm reminding you of some concept that supposedly you worked on to write midterm 2. So the size of A is always given to you by this times this. And we know that it's a very important fact that the image of L, which is the same thing as the image of A, is a subspace of Rn, just as the kernel of L, which is the same thing as the kernel of A, is a subspace of Rn. See, this Rn is this, and this Rn is this. The kernel is a subspace of the first of the domain, and the image is a subspace of the range. Furthermore, guys, if the dimension of image of A is n, and image of A is a subspace of Rn whose dimension is n. So the image has the same dimension as the space. Therefore, the image of A is the same thing as Rn. So that means the matrix, the columns of A span Rn. It means the image of A span the entire Rn, which tells you that the columns of A are a basis for Rn. You see how just by getting the determinant not zero, just by saying that the reduced row echelon form is the identity, you get like a floodgate of things. So the columns of A would be a basis for Rn. Furthermore, I can go on for 3 hours like this. What is the rank nullity theorem? We know that the dimension of the kernel of A plus the dimension of the image of A equals to n, equals to the dimension of this space. But we know that the dimension of the image, we just showed that the dimension of the image is n, because the rank is n. So that tells you that the dimension of the kernel of A is 0, which means the kernel of A has nothing in it except the 0 vector. So the kernel of A is trivial. What did we say when the kernel of A is trivial? That means, and all of this is like this, by the way, that means the transformation is injective. Remember we said this, if the kernel is trivial, if the kernel is only made of the 0 vector, then the transformation is injective. By the way, the image of A equals to Rn, that means the transformation is surjective. It means it covers the entire Rn. Most of these concepts I'm going to review with you later. I'm just showing you, if you, of course, remember the material that you had to study for midterm 2, that all of this follows from the determinant not being 0 or the matrix being invertible. Like if you get one of this, like one of these, and then you just get a floodgate of things. Like this is like all of these things follow. All of these theorems follow. So there's like more later. I want to do other topics. I don't want to keep talking about this one theorem, but there's more on this later. All right, so more on this is going to be done a little bit later. So the small takeaway from this is that if the inverse exists, the determinant is in 0, then the reduced echelon form is the identity, which means you have n leading ones, which means the rank is n, and the rank is the dimension of the image space. So the image space is n, the dimension of the image space is n, so the dimension of the kernel is 0. And this works like backwards. If the dimension of the kernel is 0, then the dimension of the image is n, then the image is all of Rn, then you have n leading ones. That means the RREF is the identity. That means you can find an inverse. That means the determinant is in 0. Like you can work it up, you could work it down, you could work any direction you want. Every one of these means all the others. Right? So let us now move to the last kind of big topic. The last big topic is eigenvalues and eigenvectors, which we're going to spend quite a bit of time on. Today we will do as much as we can, and tomorrow we're going to do a little bit more, because eigenvalues and eigenvectors is the last new topic. So we did matrices, multiplication and inverse. We did determinants. So all that is left for us to do in the new topic is eigenvalues and eigenvectors. Then I want to review this. This is done already for the midterm 2, and I've done some of it in the pre-recorded session. So I'm going to review here. So R means review. I'm going to review this with you. Then I'm going to review these. as much as we can. But the, sorry, and we did systems of linear equations also. So the only new thing that we haven't done already is eigenvalues and eigenvectors, and that's what I'm going to cover now, but after the break. So let's take a short break and then come back and do the next big topic, which is eigenvalues and eigenvectors. Right? So it is now 7:58. Let's take the full 20 minutes. Let us be back at 7:18. And wait, so at 8:18. And then we're going to go one shot till 9:30, where we're going to do eigenvalues and eigenvectors. We're going to finish today with doing eigenvalues and eigenvectors. All right. So see you in just a bit. We're back to the magical world of eigenvalues and eigenvectors. Into my mouse. There it is. Are you guys following so far? I'm a little worried, to be honest, that if you haven't reviewed any of the midterm material, that you may have been lost a little bit here. I mean, obviously, I'm gonna repeat some of the explanations tomorrow, but are you following? Is everything okay? Do you have a question for me? You've been utterly silent, so do you want me to do something differently? Do you have a request? Well, if you have, I'm right here. So, what are eigenvalues and eigenvectors? So, again, for a matrix that's n by n, this is a n by n. So there is no eigenvalues and eigenvectors for matrices that are not n by n. So lambda is an eigenvalue of A, of the matrix A, with corresponding eigenvector. Some people call it X, some people call it V. I'm gonna call it V. If, what does it mean that lambda is an eigenvalue and it has a corresponding eigenvector, V? Now, first of all, let's agree before I tell you what. V is never, ever 0. Whenever you use the word eigenvector, automatically this is not the 0 vector. You cannot have an eigenvector that's the 0 vector. That's against the laws of nature, right? So an eigenvector is always a non-zero vector. So lambda is an eigenvalue of A that has corresponding eigenvector V. This means that if you take A and you multiply it by the vector V, you're gonna get lambda times the vector V. Now, you may think this is like an easy thing or like a simple thing. It's really not. It's huge, because this is a matrix A that you're multiplying it by a vector V, and it's as if you took a number, lambda as a number, and you multiplied it by vector V. Like, think of A as like 1,000 by 1,000 matrix. You multiply it by a certain vector V, it's as if the result is 2 times V. So the 2 summarizes the effect of a matrix that is 1,000 by 1,000, right? So it's a huge thing. So lambda is an eigenvalue of A. That means if you take A and you multiply it by V, it's the same thing as you take lambda multiplied by V. Now lambda is the eigenvalue and it's a number. I want to insist that it's a number. And V is the eigenvector is V. I'm going to say it again. I never tire of saying the same important stuff. V is never equal to 0. An eigenvector is always, let's just be positive about it, an eigenvector is always not equal to 0. Never equal to 0. So how do we find the eigenvalues? How do we find the eigenvectors? What's the whole story there? I'm gonna explain it to you briefly. So if AV equals to lambda V, that means you have AV is minus lambda V is equal to 0, the 0 vector. Now, I want you to pretend that there's the identity here, and we are allowed to put the identity here because the identity is like 1 for matrix multiplication. And then we factor out V, we get A minus lambda I V is equal to 0. And because V is non-trivial, V is not all zeros, that means that this matrix cannot be invertible. That means that the determinant of A minus lambda I has to be equal to 0 because A minus lambda I is not invertible. Now, if you don't fully get why, I will say it, but you don't really need to know it. Like you can live your entire life not knowing it and you'll be fine. Because if A is invertible, if this matrix was invertible, see, if the matrix A is invertible, so if A minus lambda I is invertible, that means the kernel of A minus lambda I contains only the zero vector. But then this vector is in the kernel, right? You multiply this by this vector and you get zero. So V happens to be in the kernel, right? Because V is a non-zero vector in the kernel isn't just the zero vector, so this is not invertible. Right? Again, the importance of what we said here, that if A is invertible, that means the kernel of A can only contain the zero vector. Again, what's the kernel? The kernel of A is all the vectors V such that when you multiply A by V, you get zero. So it's all the vectors that you multiply A by to get zero. So what's the kernel of this matrix? What is the kernel of the matrix A minus lambda I? The kernel of this matrix is all the vectors V such that if you take A minus lambda I times V, you get zero, right? This is the kernel of this matrix. Now, I found a vector inside the kernel that's not zero. That means the kernel of A, the dimension of the kernel is bigger than or equal to 1. There's at least one vector in it. You get what I'm saying? Like at least there's this vector. So it's not empty. It's not empty. The kernel of A is not empty, meaning it's not just the zero vector. There is something. So because there's something in it, that means this matrix is not invertible. Because if it was invertible, the kernel would be empty. And I add I into the equation, my dear Johnny, because we can't say A minus lambda. How do you do a matrix minus a number? Right, I can't say A minus lambda, right? A is a matrix, lambda is a number. So I need to do a matrix minus a matrix, right? So that's why I add in a 1 there. Kind of, let me bring you back to your high school days. Let's say you want to factor x squared minus x. How do you factor x squared minus x? You factor out an x and you get x minus 1. But where do you get that 1 from? Well, that one was kind of there. That one was already there, but we didn't actually write it down because nobody says 1x. You understand what I mean? I'm kind of using the same idea here. Do you get that? So, in summary, if you want to find the lambdas, if you find the eigenvalues, thank you for letting me know, Johnny. So if you want to find the lambdas, what you want to do is you want to solve the determinant of A minus lambda I equals to 0. This is what we call the characteristic equation of A. This is how we find the lambdas. Now, to find the eigenvectors, to find the V's, so for each lambda, because each lambda will have its own eigenvector, replace lambda in A minus lambda I and find the kernel of A minus lambda I. What does it mean? Find the kernel of A minus lambda I. This means you solve A minus lambda I times x equals to 0 Again, in layman terms, in English, this means you just solve the system A minus lambda I with a bunch of zeros. So finding the eigenvectors is like finding the kernel of A minus lambda I, which means solving A minus lambda I x equals to 0. Okay, this is a lot of words. Let's practice. So, example. Again, our goal is not to become the world's experts in linear algebra. Our goal is to ace our final. So, our goal is to be able to solve the problems that they throw at us. So, let's practice solving a problem. Let's take A equals 2, 1 minus 3, 1, 5, and we want to find all the eigenvalues and all the eigenvectors. Fair? So how do we find the eigenvalues? To find the eigenvalues, I need to find, I'm going to write it again. To find lambdas, we need to solve the determinant of A minus lambda I equals to 0. Fantastic. So what's A minus lambda I? I know what A is. What's lambda I? Lambda I is lambda times the identity. So this is lambda 0, 0, lambda. And A minus lambda I, that's 1 minus 3, 1, 5, minus lambda 0, 0, lambda, which is 1 minus lambda minus 3, 1 minus 3 minus lambda. So that's A minus lambda I. Now, what's the determinant of A minus lambda I? Now we know determinants. The determinant of A minus lambda I is 1 minus lambda, 3 minus lambda, plus 3. And you want to make this equal to 0. So this would be lambda squared minus lambda minus 3 lambda minus 4 lambda plus 3 is plus 6 equals to 0. I'm pretty sure everybody knows how to solve this, either the quadratic equation or factoring. I'm going to go to factoring. Lambda minus 2 lambda minus 4 equals to 0. Now, so lambda equals to 2 or lambda equals to 4. Always choose lambda 1, the bigger in size. So in here, lambda 1 is equal to 4 and lambda 2 is equal to 2. Even if lambda 1, even if this was plus 4, still choose lambda 1 equals to minus 4. Again, the bigger in size. Make it a habit to choose lambda 1, the bigger in size. So we found the eigenvalues. Do you want me to show you a trick? I don't know if they cover this with you or not, but I can give you a trick. I don't think you do this in APSC 174. So this is a side note to check your work. When you multiply the product of the eigenvalues, that's the determinant of A. 2 times 4 is 8. You can check here the determinant of A equals to 8. So you're good. Right, so this is a quick test to check if your lambdas are fine. And by the way, the sum of the eigenvalues, that's the trace of A. I don't think you do trace, but trace is a very easy definition. It's the sum of the main diagonal. So 4 plus 2 is 6. 1 plus 5 is 6. Now I'm 1,000,000% certain that I got the right answers. So the sum of the eigenvalues is the sum of the main diagonal, and the product of the eigenvalues is the determinant of the matrix. That's how you know that you're 100% correct. So now finding the V's. For lambda 1 is equal to 4, I want to find the eigenvectors, and then, sorry, let's give a title here. So now finding the eigenvectors. So for lambda 1 equals to 4. Look, there's many ways of saying it. Some people say we are finding the eigenvector or vectors corresponding to lambda 1 equals to 4. That's one way of saying it. Another way of saying it is finding the kernel of A minus 4i. Right, the kernel of A minus 4i, because the kernel of A minus lambda I, but lambda is 4. Some, if you want to be like really, you know, I don't know what the word about it, but if you want to be really like annoying in math, or if you want to be really a nerd, you can say, I am finding a basis for E4. And you're going to tell me, what is E4? This is the eigenspace of vectors of corresponding to lambda equals to 4. Again, it's all meaning the same thing. You're finding V. So finding a basis for the eigenspace, or finding the kernel of A minus lambda I, or finding the eigenvectors corresponding to lambda 1, all of those mean exactly the same thing. You're finding V. Now, how do you find V? Remember, you take lambda and you plug it in here. So this would be 1 minus 4 is minus 3, minus 3, 1, 1, 0, 0, and you add 0, 0 because you're solving for the kernel. When you solve for the kernel, you put 0, 0 on the right side. Please listen carefully. You always get a 0 row. If you don't get a 0 row, you've done something wrong. You always get a 0 row. So if you reduce this matrix, you realize it's 1, 1, 0, 0. Now you know how to solve this. You know how to find the basis of the eigenspace. You know how to find the basis for the kernel. This is finding the basis of the kernel, right? You know how to do this. You've done them in midterm 2. So y didn't get a leading 1, so y gets a parameter. X is just minus y, so x is minus t. So my solution is t times minus 1, 1. And look, you can choose any value of t you want. So any value of t works. So for example, you can say v1 is equal to, you can take t equals to 1 minus 1, 1, the simplest version. So again, how do we answer this, or what did we find? Some people, we said, so V1, some people say V1 is the eigenvector corresponding to lambda 1 equals to 4. So we can say V1 equals to minus 1, 1. That's one way of saying it. One way of saying it is that the kernel, so if a basis for the kernel of A minus 4i is that vector, minus 1, 1. Which means, by the way, the dimension of the kernel of A minus 4i is equal to 1, because there's one vector in the basis. Great. Or we can say, so this is all or, you can say this. or you can say this, or you can say that V1 equals to minus 1, 1 is a basis for E4. Again, E4 is the eigenspace of vectors corresponding to lambda equals to 4. So E4 is all vectors such that A times V equals to 4V. Basically, the eigenvectors of the eigenvalue lambda equals to 4, right? This is all just saying the same thing, right? I mean, you can even say E4, the eigenspace corresponding to lambda equals to 4 is the span of minus 1, 1. Right? See, all of these, I promise you, just mean the same thing. So don't let the linguistics confuse you. So let's do it for lambda equals to 2. For lambda 2 equals to 2, we're going to plug it here. So minus 1, minus 3, 1, 3, 0, 0. One row will cancel, so for sure you'll get 1, 3, 0, 0, 0, 0. So y doesn't get a leading one, so y gets a parameter. X is minus 3y, so minus 3t. So my solution is t times minus 3, 1. Pick whatever t you want. So let's call v2 equals to minus 3, 1. Again, everything. Oh, no. What do you mean, is it a random matrix, Johnny? I plugged lambda equals to 2 here. Right? You take the eigenvalue, you plug it here, and you add 0, 0. Was that your question? Right? You're finding the kernel of A minus 4i. So this is the matrix A minus lambda I. You're putting lambda equals to 4 here to make it A minus 4i. And the kernel is, when you solve it, equal to 0. Okay, so final note before we do another example. E lambda, I'm going to say this again. This is the eigenspace. This is the eigenspace corresponding to lambda. What is this? This is all the vectors V such that AV equals to lambda V, meaning the eigenvectors, right? It's just the eigenvectors. This is the span of the eigenvectors, vector or vectors that correspond to lambda. Now, this is the kernel of A minus lambda. We said all of this earlier. I'm just summarizing it here. By the way, the eigenspace corresponding to lambda is a subspace of Rn. Of course, if A is an n by n matrix. So if A is an n by n matrix, that n matches this. So the eigenspace is a subspace, and you can check it. It's quite fun. It is an eigenspace. It contains, because it's a span, any span, right? This is the span of the eigenvectors, like v1, whatever, right? So anytime we have span, it makes it a subspace. Okay, I think we're all ready for a second example. So let's see. Here we go. Where is this from? Okay, I'd like to do one from a final. I have a bunch that I prepared, but I'd like to do one from a final. So APSC 2020, what did they ask? Determinants we did. There we go. Beautiful. I have a bunch of examples that I prepared, but I like always to do one directly from your final so you can see sort of that I am doing the same thing that they ask you on finals. So find the characteristic polynomial of A. Okay, what is the characteristic polynomial of A? We talked about this. It's the determinant of A minus lambda I. This is the polynomial alone. If you make it the determinant of A minus lambda I equal to 0, then it becomes an equation. It becomes the characteristic equation. If you just want the polynomial, then don't make it equal to 0. Great. So what is A minus lambda I? This is, I'm too lazy to copy this, and it's been a long, long day. So allow me to just cheat a little. A minus lambda I, so lambda 0, 0, 0, lambda 0, 0, 0, lambda. By the way, did you do this in class already or not yet? Have you covered this in class? I know we're doing this as one of the earlier sessions. Have you done this in class? Okay, well, you don't know, so I don't know either. So let's see on what column. So now we're going to take the determinant of A minus lambda I. So we clearly see column 2 as a perfect place to expand. So plus, minus, plus, minus. So we're only interested in the middle term. So this is plus 5 minus lambda times the determinant of what's left, which is 14 minus lambda, 15 minus 6 minus 5 minus lambda. So this is equal to 5 minus lambda times 14 minus lambda times minus 5 minus lambda plus 90. So this is 5 minus lambda actually what minus plus lambda squared minus plus 5 lambda minus 14 lambda is minus 9 lambda minus 70 plus 90 is plus 20. So this gives you 5 minus lambda, lambda minus 5, lambda minus 4. And verify that 4 and 5 are roots of the polynomial. We did. If you make this equal to 0, then you're going to get lambda 1 equals to 5. It happens twice. I want to insist that you see this. It happens twice. And lambda 2 is equal to 4 once. Now, for your course, twice or 3 times or 17 times won't make a difference because you really don't do much with eigenvalues and eigenvectors. Johnny asked the $1 million question earlier. What do I use this for? And really, there's very, very little application. So it won't really matter yet. But when you take higher courses, this will matter a lot. So when you take higher courses, this will matter a lot, whether it's twice or 3 times or 4 times or whatever. Okay, so for part B, I would like to find the basis for E5. So I'm going to take 5. I'm going to plug it here. And then I am going to put 0, 0, 0. So 9 0, 15, 0, 0, 0. You see your row of zeros? Minus 6, 0, minus 5 minus lambda is minus 10, 0, 0, 0. Are you ready for this? If you reduce this matrix, you will see that you get 1, 0, 15 over 9, so 5 over 3, 0, 0, 0, 0, 0, 0. So when you reduce this matrix, you don't get one row of zeros, you get two rows of zeros. And that's fine. See that twice? That's kind of have something to do with it. It's not necessary that if it's twice that you get two rows of zeros. It's not a guarantee. But when you get two rows of zeros, you must have started with twice, right? See here, this doesn't imply this, but the two rows of zeros imply it, right? Anyway, you don't actually need to worry about any of this. So y did not get a leading one, z did not get a leading one, and x is equal to minus 5 over 3z. So the solution is going to be a vector for s and a vector for t. So this is 0 minus 5 over 3. Y is 1s 0t, and z is 0s 1t. So what would be a basis for E5? Again, you can pick any value of s and t you want. For the s part, let's pick 0, 1, 0. But for this part, let's make t equals to 3. So you get rid of the fractions. So this. Again, any value of t works. So what's the dimension of E5? It's the number of vectors in the basis, and the dimension of E5 is 2. Okay, can you tell me what E5 is again? Tell me what E5 is. E5 is the kernel of A minus 5R. This is all the vectors V in R3 such that A times V is equal to 5V, right? 5, 5, 5. Now for E4, so same story, really you're just going to plug it there. So that would be 10, 0, 15. 0, 1, 0, and minus 6, 0, minus 9. When you reduce, you are going to get 1, 0, 15 over 10, which is 3 halves. 0, 1, 0, 0, 0, 0. It doesn't take long to reduce. I'm sure you're able to do it. So now only z gets a parameter, y is 0 from this line, and x is equal to minus 3 halves t. So I get one vector with t, minus 3 halves 0, 1. So we want a basis for E4. That would be, let's take t equals to 2. So the vector minus 3, 0, 2. Which means the dimension of E4 is equal to 1 because there is one vector in the basis. Do you guys follow what I'm saying? All right. So let me ask you a couple of questions. So here are a couple of questions to just make sure you understand what I'm talking about. So let's take a matrix A, and A is 14, 0, 15, 0, 5, 0. You may recognize this from before. I am using the same matrix. And I'm telling you that V is an eigenvector. So V, which is minus 3, 0, 2. I'm telling you that V is an eigenvector. Here's my question to you. What's lambda? Well, because we know that V is an eigenvector, we know that AV equals to lambda V, right? Now, if AV equals to lambda V, then let's find AV. So what's A times V? What's A times V? Now we can do the method of linear combinations of the columns, or we could just multiply. This is minus 42 plus 0 plus 30 is minus 12. And really all I need is the one entry. I don't care about all the others, because this is AV and this is supposed to be lambda V. So what's lambda? You really just need one entry. So what's lambda? If you continue here, you're gonna get 0 and 8, but you really don't need those, right? Because what's lambda? What should lambda be? So when you multiply it by minus 3, you get minus 12. The answer is lambda equals to 4. You get what I'm saying? Like, you don't actually need all this. You just need one entry, and that'll tell you what the lambda is. Now, a couple of notes that are important about eigenvalues. So if we have lambda if lambda is an eigenvalue of A that's corresponding to the eigenvector V, meaning A V equals to lambda V. So if lambda is an eigenvalue, blah, 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 then we can deduce eigenvalues for powers of A. So, for example, then lambda to the power k is an eigenvalue of A to the power k corresponding to V. The eigenvector doesn't change. One over lambda is an eigenvalue of A inverse, again, corresponding to V. So whatever power you put on the eigenvalue is the same power you put on the matrix, because this is, by the way, lambda to the -1, and lambda can't be 0. If a matrix is invertible, then lambda can't 0. Like lambda plus C is an eigenvalue of A plus CI. Again, corresponding to V. C is just the constant, so C times 1, let's say, and that's how you get C times the identity. Right? So, an example, like an example in numbers. So if I tell you that lambda equals to 2 is an eigenvalue of A corresponding to V is equal to 1, 3. Then what would be the eigenvalue of A cubed? So to get the eigenvalue of A cubed, the eigenvalue of A cubed, one of the eigenvalues, of course, because this is one eigenvalue, not all the eigenvalues. Then one eigenvalue of A cubed is 2 to the power 3, which corresponds to, again, V equals to 1, 3. Look, you guys, multiplying by an eigenvector is an incredibly nice idea. Multiplying by an eigenvector. When you take A and you multiply it by an eigenvector, it's as if you multiplied the eigenvector by a number. This is what makes it super awesome. When you multiply a matrix by its eigenvector, it's really just multiplying the eigenvector by a number. That's the whole story there. So, look, in 2020, they asked a nice question that covers this. So I'm gonna look at 2020. Look, so this is a nice example that illustrates the use of eigenvalues and eigenvectors. Look, let's go through this slowly. So let A be a matrix that is 2 by 2. We have V1. They tell us that V1 is an eigenvalue. V1 is an eigenvector. V2 is an eigenvector. They are asking us to find their eigenvalues. We did this, right? I showed you how to do this. So A times V1 gives me 4 over 5, 3 over 5, 1 over 5, 2 over 5, times 3, 1. And all I need is the first entry. So that's 12 over 5 plus 3 over 5, which is 15 over 5, which is 3. I don't even need to know the second entry. So what is lambda? Lambda is equal to 1. Right? What times this? Right? See this? Okay, let's do this. So if you multiply, you're gonna get 3, 1. Right? But this is A V1, which is supposed to be lambda 1 times V1. So this is supposed to be lambda 1 multiplied by 3, 1. So what should lambda 1 be? So you get an answer of 3, 1. Basically, lambda 1 is equal to 1. Let's try it for the second vector. What is A V2? It's this times 1 minus 1. I remind you that this is supposed to be lambda 2. I'm going to put in the answer here. But this is supposed to be lambda 2 times V2. So this is 4 over 5 minus 1 over 5, minus 3 over 5 is 1 over 5. I don't need to know the second answer. What's lambda 2? Right. Lambda 2 is what? So I would get 1 over 5 there, and lambda 2 is 1 over 5. Do we see that? Now, look at how nice this question. They're telling us to find A to the power 2 times V1. Look, this is incredibly nice. Am I going to find A2? What if they said A to the power 8 V1? Are you going to find A to the power 8? No, you won't. Look, I'm going to keep it as A2. A2 V1 is A times A V1, yes? Tell me something. What is A V1? V1 is an eigenvector. What is A V1? That's lambda 1 V1. Which means this is A times lambda 1 V1. And lambda 1 is a number, so you can move it to the front. So you have lambda 1 times A V1. One more time, A V1 is lambda 1 V1. So this would be lambda 1 V1, and this would be lambda 1 squared V1. And lambda 1 is 1, so basically that's just V1. Look, you guys, A to any power times the eigenvector V1. You do the same process I did earlier. You get lambda 1 to the power k times V1. Remember what I told you earlier? If lambda is an eigenvalue of A with corresponding V, then lambda to the k is an eigenvalue of AK corresponding to V. What does this line mean? This means that if you took A to the power k and you multiplied it by V, you get lambda to the k multiplied by V. This is the eigenvalue of this matrix with corresponding vector V. That's what this means. So, this is in general. So if you want to do A squared times V2, this is basically lambda 2 squared times V2. And lambda 2 is 1 over 5 squared times V2. Okay, now this is a nice question. Write W as a linear combination of V1 and V2. So this brings us back to midterm 1. V1 is 3, 1. V2 is 1 minus 1. So how do we write 9, 7 as a linear combination? So 9, 7 is equal to A times 3, 1 plus B times 1 minus 1. So that gives us a system 3A plus B equals to 9, and A minus B is equal to 7. You solve this wherever way you want. You're going to get A, 4A is 16, so A is equal to 4, B equals to minus 3. So 9, 7 is 4V1 minus 3V2. And look how useful this is. So for W in part A, they're asking us, come on. For W in part A, they're asking us to do this. What's the limit as A and W? But look, before we do the whole thing, what's A n times W? Alone, what is A to the power n times W? This is what they want us to find, right? And we just found that W equals to 4V1 minus 3V2. So this is A to the power n times 4V1 minus 3V2, which is 4 times A to the power n V1 minus 3 times A to the power n V2. And what did we talk? Well, what did we say when we multiply a matrix by the eigenvectors? This is 4 times lambda 1 to the n V1 minus 3 lambda 2 to the n V2. Now lambda 1 is 1. Lambda 2 is 1 over 5. So this is 4V1 minus 3 times 1 over 5 to the n v2. Now what happens when n goes to infinity of this entity right here? When n goes to infinity, this would go to 0. So the answer is 4v1. And again, it all lies in the idea that if A times V is equal to lambda V, then A to the power K times V is lambda to the power K times V. I've said this a few times now, and I'm saying it again. Right? I think they, not I think, I'm sure they asked you one where they gave you tanks. Was it in 2021? There we go, the famous tanks problems. See, this is exactly what we just did. This is exactly what we just did. They just gave it to you in a way to like maybe stress you a little. This is 2021. Let's go through this together. Okay. Consider the two tanks X and Y shown at the right. Tank X contains 500 liters of liquid. Tank Y contains 1,000. Every minute, 100 liters cross from here to here. Define Xn and Yn to be the mass in kilogram of a chemical dissolved in the liquid in tank X and Y respectively. We start the system with this. After analyzing the system, you find that this is the solution. So, right, so there's a way to do this. We're not going to get into the analysis of how to do this because you don't really need to know how to do this. What you need to know is the rest. So they gave you that Xn plus 1, Yn plus 1. So the next n, so this is at time t equals to 0, x0, y0. Now, what n is kind of the time after 1 minute, after 1 hour, after n minutes. So they gave this in 2 minutes. So after n minutes. Okay, so let's go through the problem step by step. So A, verify that these are eigenvectors. Find their corresponding eigenvalues. We've done this a few times now. So 0.8, 0.1, 0.2, 0.9. Multiply it by 1 minus 1. We are going to get something. And that's supposed to be lambda 1 times 1 minus 1. So this is going to be 0.8 minus 0.1. That is going to be 0.7. I really don't care what this is because that tells me right away that lambda 1 is 0.7. Just to be sure, compute it. Maybe you did a mistake and you didn't because this one is minus 0.7. Now, what is 0.8, 0.1, 0.2, 0.9 multiplied by 1, 2? This is going to give me a vector, and that vector is supposed to be lambda 2 times 1, 2. So this would be 0.8 plus 0.21. So definitely this is going to be 2. So lambda 2 is equal to 1. Great. Write the initial condition as a linear combination of the eigenvectors. Okay, so we want to write 95, 25 as A times 1 minus 1 plus B times 1, 2. So A plus B is 95 minus A plus 2B is 25. Now you can solve this any way you want. I would just simply add them. You get 3B equals to 120. So B is equal to 40. So A is equal to 55. So 95, 25, which is x0, y0, is equal to 40 1 minus 1. No, it's 55, 1 minus 1 plus 41, 2. Okay, find a formula AN times 95, 25. So remember, this vector we called it W before. This is the vector that we called W before. Before, that was called W. So look, instead of saying a to the power n times 95, 25, we're going to replace 95, 25 by 55 V1 plus 40 V2, which is this. This is V1, this is V2. So we're going to write this as 55 a to the power n times V1 plus 40 a to the power n times V2. Now, what did we say is a to the power n times V1? That would be lambda 1 to the power n V1. And this would be lambda 2 to the n times V2. So that would be 55 times 0.7 to the power n V1 plus 41 to the power n, which is 1 V2. And what do you think they ask now? The limit as n goes to infinity. So part D, what is the limit as n goes to infinity of AN 95, 25? This is the limit as n goes to infinity of this quantity here. This would go to 0 because it's less than 1. So this would be 40 V2, which is 40 times 1, 2, which is 4080. So that means if you leave the tanks running for a long time, there will be 40 kilograms of salt in the first tank, and there will be 80 kilograms of salt or chemical or whatever in tank 2. That's the behavior of xn and yn when n goes to infinity, which means after a large amount of time. That's, ladies and gentlemen, eigenvalues and eigenvectors. Let's look, what's the most recent one I have? 20. Do I have 2022? Have they released 2022? I don't seem to have it anywhere. Let me double check if I saved it in my work folder. I don't see the 2022 one. Have they released the 2022 midterm 3? I only see 2021. Let me double check one more place. Here we go. Nope, that's not it. I don't see it. I'm gonna look for it for tomorrow because I thought I have it. Let's see. Midterm 2. Yeah, I have all the midterm 2s. I don't seem to have the I don't seem to have the final exam. So maybe I'll reach out to people, or maybe you can send it to me. Was the question is, was the final? It wasn't the final in 22. Oh, actually it was. Was the final of 2022 released? And if it is, maybe can you send it to me so I can double check it? And if they're interesting problems, we will definitely do that. Right, so that completes everything that we set out to do and then some. You've been quite silent, so we've been moving at a faster than average rate because I'm not slowed down by questions. I wish you would ask me more questions, and that covers basically the entire part after midterm 2. So tomorrow I'm gonna start by reviewing this, and then I will do a review of all of these concepts, of course, and I will answer. So we did the thanks. And of course, if you have questions about these, if we run into any interesting questions that we haven't done them, I will gladly solve them with you. Do you have any other questions, any comments, anything at all before we call it a night? No, you don't seem so. So thank you very much. And to share anything with me, here is my email one more time, Antoine@prep101.com. Thank you very, very much for coming. I hope this was super helpful to you, and I shall see you tomorrow. Head office, thank you very much, and take care.